chemical cycling in general. And I'm actually ahead of myself here because we've already given you some biogeochemical cycling. That's what basically the nitrogen and phosphorus stuff that I had to put up because I was at home waiting for the air conditioner guy. Okay, so what does this mean, first of all? And all it is just cycling of elements you're moving through three different phases. So, and bio is the biotic phase, and the abiotic phase is the geo and chemical. And I'll explain what each one of those things are. So biological, geological, chemical. Okay. And the ecosystems, of course, we're talking about here are lakes and rivers. So nothing exciting in there. Okay. This is sort of the generalized model. I'm going to use some terms. These are not special. These are terms in general, and they are somewhat counterintuitive. So you have biological components, you have chemical components, and you have geological components. So basically, this is, anything is part of living matter is the biological component. Chemical component is non-living but extremely available. Okay, so basically, think about photosynthesis in a plant taking up carbon dioxide. It's gone. Well, actually, not carbon dioxide. Let's say we were talking about nitrogen. So this would be like ammonium or nitrate being taken up by plants. Is a good example of that. Okay. This is basically long-term storage, geological. And when you see geological, you think rock, but don't always think rock, because in the nitrogen cycle, the geological component is the air. So it can change. Okay. So as I was just talking about, movement of chemical things from the chemical to the biological is basically called, the term for that is assimilation. It's been assimilated, moved up with that. The opposite of assimilation with biological things, with a chemical, if you think about that, decomposition is a good example of that happening. Okay. But the term is mineralization for that. And this is one of those counterintuitive terms because you're thinking geological is mineral, but it's not. It's basically mineralization is going from the biological to the chemical. So geological components then to the chemical. Okay, this is so basically when I think about it here, I think of, for example, when rock starts to weather, and it frees up calcium and nitrogen, calcium and magnesium. That's this movement here. And so if you think of this stage, it was immobilized, and now you have mobilized it, moved it out this way. The other way around is basically known as deposition. And again, deposition is used for many different things. So this is the way I'm defining deposition here is maybe it's different than what I would be defining it if I was talking about sedimentation. And then the last big movement is some things can move directly from biological to geological. This one, this is easy. We call that fossilization. So these are sort of the standard terms of moving from here. Each one of the cycles has its own term. So like on the nitrogen cycle, movement from biological to chemical is called a modification in your book. So I've given you all those terms. When you look at the videos, you'll see that term there. So that and so they have different and then this is known as immobilization, going that way. So okay, examples of biogeochemical cycle I've already covered. I covered water really, and will cover it. Already covered. I'm about to cover this. I have covered nitrogen and phosphorus and a little bit on sulfur. Sulfur's pretty boring, but I've given you information on those already. So today I'm going to mess with carbon. Okay, and if you think about it, everything cycles in one way or another. That's the whole idea of ecosystems. We talk about ecosystems. Energy flows through ecosystems, comes in somehow as fixed sunlight, leaves somehow as heat. So it comes in and goes out. But the nutrient elements cycle in some ways or other. Okay, so get to what I want to talk about today, and that's carbon cycling. Carbon is kind of interesting because it's a very important structural atom. We are carbon-based life forms. Everything on Earth is based on it. And the other thing about carbon, remember I say energy flows through that, and as energy moves through it, that energy is part of a carbon bond somewhere. that's where the energy's coming from. So again, you think about when you eat sugars, when you eat sucrose, you're actually eating glucose and fructose, and the energy you're going to get from them comes from those carbon bonds. So this carbon is cycling at the same time you're flowing energy. So they track together very well. Okay. So carbon is fixed. In other words, it goes from the abiotic form to the biotic form during photosynthesis. So CO2, if you think about it, is pretty much I guess you could consider it the chemical form. And so it's abiotic and it becomes fixed into glucose, which then becomes part of the structure of the producer. And then it's transferred between trophic levels. Something eats the primary producer as a primary consumer, passes to a secondary consumer, tertiary consumer, around and around. So those are biotic to biotic transfers there. And eventually, as the energy is released from the system, so is the carbon is released from a biotic form to an abiotic form, it's released back into carbon dioxide. So basically this is the movement between the biological and the chemical, back and forth. So because of the close association with energy, humans, who happen to be energy hogs, have affected the availability of energy by increasing it greatly, and in the process, that's impacted carbon cycling. Okay. So again, here's my generalized model. So here's, if I take this model, and I'm going to change these names now for the names that are used for the carbon cycle. Okay. So mobilization is still mobilization. Okay. So the geochemical form, or the geologic form, is primarily carbonates. Okay, carbonates are CO2 or HCO3, H2CO3, HCO3 with a -2 charge. So carbonates are part of that, and petrochemicals are the other part of that. So tars and everything and all that. Okay. Again, as I mentioned before, the chemical component is primarily carbon dioxide. And the biological component is still the biological component, anything that is this way here. So the movement from CO2 into biological is photosynthesis, and the movement back is going to be cellular respiration. Mobilization is mobilization, as I mentioned before. And this is still fossilization, and this is still deposition in these forms here. So that's basically how the words have changed a little bit here. Okay, so the movement of mobilization primarily takes place through combustion. So not so much the carbonates, but the petrochemicals, they're burning, it goes that way. Okay, human impacts on the carbon cycle. Here it is again, set up again, simulation. So what's happened through human activity, assimilation is going down. The movement of CO2, the movement of CO2 into organic matter has gone down. What's caused this is primarily the loss in many habitats of primary producers. Trees are being cut down, removed. So you don't have as much photosynthesis going on a global scale. Mineralization, cutting these trees down. So this is going up. We think about cutting these trees down, burning these trees, that's going up. So the movement out of here this way is slowed down, but the movement back into here is going up. So this component is increasing in size. Mobilization from here, in other words, turning petrochemicals into carbon dioxide through combustion, has gone up too. And then where else I got here? Deposition probably hasn't changed much at all. Fossilization probably hasn't changed much at all. But the general thing is that this box is growing bigger and bigger. So we're seeing this increase in carbon dioxide. And I don't know if you've heard of the Mauna Loa database. Has anybody heard of the Mauna Loa database? I mentioned it back in wetlands. Okay. monolith database is basically what it is. It's every day on Mauna Loa, which is a mountain island in Hawaii, the top of that, since they're coming up, we're starting at least 80 years, if not longer. Every day, someone grabs a sample of air and analyzes it for carbon dioxide. And so again, what we see is carbon dioxide has greatly, over those 80 years, the amount of carbon dioxide in the atmosphere has increased greatly. If you look at the Mauna Loa database, it's pretty cool. It looks like a sawtooth going up. And it's sawtooth because in the summer, carbon dioxide levels in the northern hemisphere in the summer, carbon dioxide levels are lower because of all the photosynthesis going on. In the winter, decomposition, so there's this yearly cycle, but the overall trend is clearly rising. So the amount of carbon dioxide in the atmosphere is clearly increasing. That's not a question. Okay. The atmospheric temperatures are clearly increasing. That's not a question. The question comes into, is that carbon dioxide the result? Are those rising temperatures the result of the carbon dioxide? And that is hard to test. I mean, it's kind of, the only way to test that would be to have 6 Earths. 3 of them you treat with carbon dioxide and 3 of them you don't. See what happens. So we can't really do that. But it's compelling evidence that it's a strong correlation. Okay, forms of carbon in water. So where we find it? Okay, so carbon dioxide in water. It can exist suspended as carbon dioxide, but and of course we talked about oxygen. The oxygen only exists in the suspended form. It does not truly dissolve. Carbon dioxide does. Okay, so carbon dioxide, there's not a whole lot of carbon dioxide in the world, thank goodness. It's a very small component of the Earth's atmosphere. These exact numbers are not important. Okay, and then what it does is when it hits the water, it truly does dissolve. Okay. Some of it will remain as CO2, but a lot of it will take on to another form depending on the water. Okay. So sources of carbon dioxide in water. Well, one is simple. If you have an atmosphere, you have some. It's not much, but you have some in the atmosphere. It's going to be greater than the amount in the water if you have a diffusion gradient. So it comes straight in from the atmosphere. And then you have things that live in the water that are doing cellular respiration. If you remember, I talked about the physical gill, how it works. It's a fine example of when a fish is ventilating, it's basically losing carbon dioxide to the water that way. Okay, besides carbon dioxide, once it dissolves, it becomes dissolved inorganic carbon. And these are the different forms you find in water. Carbon dioxide, like I said, carbonic acid, and these, I've already covered some of this in lab. This one I got off a tangent last time we met as a lab, so this is where I'm going to come back and officially give it to you. Carbonic acid, this is bicarbonate. This is carbonate, and I'll talk more about these a little bit later. Those are the forms of inorganic carbon. Okay. So what happens is, so these are the sources. Again, the sources of these are atmosphere and cellulose roots. The sinks, how is it lost from the system? It's through photosynthesis. Aquatic things doing photosynthesis are pulling CO2 out of the water and using it. In water, there is also dissolved organic carbon. So when I think of dissolved organic carbon, I think of things like tannins. Tea is a good example of dissolved organic carbon. Basically is in the system here. So what these are they pretend to be organic acids, and they're fairly stable. They don't fall apart. So many of them come from the soil, so they're referred to as humic acids. Okay. And much of this stuff is there because it's not going anywhere because nothing really can eat it. So we call it refractory material. Refractory means that things can't break it down. Okay. Contrast that with things that break down easy. So if I have tannins in water, they're going to stay there. If I then mix in some sugar, it's going to get taken up right away. Something's going to break it down. Sugars are easily used by bacteria. They are labile. So these are two terms that we use referring to how stable an organic compound is. So, besides truly dissolved organic carbon, any particular organic carbon that's smaller than 0.45 microns is also considered dissolved. It's so small it's considered dissolved. This is the magic number here, 0.45 microns. So, anything above 0.45 microns is what we call particulate organic carbon. Okay, so you are particulate organic carbon. Okay. Dead things are particulate organic carbon. Non-living things, so feces and dead leaves, dead fish, all these sort of things are particulate organic carbon. Okay. Discarded parts of organisms, the leaves. Okay. And so putting all these together, here's what we got here. So basically, carbon cycle, here's my lake. This is my lake. I do that all by myself. Okay. So you have, and this is made just sort of just a generalized picture. So up in the lake you have particulate organic carbon up in the lake, and then on the bottom you have particulate organic carbon. So this is in the water column itself, we say. So it's littoral or limnetic, and this is what's on the bottom. Okay. I have dissolved organic carbon and dissolved inorganic carbon. Okay. And so into my lake, I could have coming in from another, we used this term allochthonous before. So allochthonous is anything from another habitat is pulled into your habitat. So for example, in a lake, leaves are constantly falling into a lake. That's an allochthonous input. So leaves falling into the lake would be right here. Maybe some water coming in as overland flow right here. We have both of these in it. So that's inflow into the lake coming into the littoral material here. I got carbon dioxide exchanging with the atmosphere. Okay. This inorganic carbon, primarily CO2, is being taken up. So this is carbon coming in from the outside in. This is carbon being fixed right inside the habitat, so we call that autochthonous. So what we're doing is we're making little algae or something like that, and that little algae is going to be particulate organic carbon because it's alive. Okay. And that could turn around. Living things are going to lose back to respiration here. Okay. Heterotrophy here. What this means is some of these critters are actually utilizing dissolved organic carbon to make themselves. If it's dissolved, if it's labile, they can take it up, and so again we're fixing it back into particulate. And a lot of these things, and Dr. Greenwood usually talks about that. I don't know if she has mentioned it yet or not. These things are very sloppy, and as they're fixing all this carbon, that leaks out of them, a lot of it. And so they take this up, they're growing, but they're leaks right back out. All right. So these flows are just, so a lot of the stuff that falls on the bottom is going to be staying at the bottom. This is heading for fossilization, but there may be some sort of currents and all that that'll resuspend the dissolved organic and inorganic. And then a lot of it comes settling down, precipitates out of the system here. So that should be it. And then the sedimentation this way. So yeah, that's the complete flows. I think I gave you this. Well, I'm going to give you this picture because I've given you the lectures. So, Alec, I think you might have heard that, but I've uploaded this lecture I'm giving you right now is uploaded as a lecture with sound on it. So everything I'm doing now, you can start again. It'll probably be better than I'm doing today. Okay. All right. So where do we find carbon in the world? Well, in one of the geologic forms, rock. And it primarily exists as carbonates. Calcium carbonate, magnesium carbonate are the big ones. So calcium carbonate we know of as limestone. Magnesium carbonate we know of as dolomite. So these are a lot of rock. It's in the atmosphere again as carbon dioxide. Not a big source, but there is some in the atmosphere. And again, it's a low concentration, except as I explained, it's steadily increasing. Okay. Oceans are full of it too, also, but primarily as dissolved inorganic carbon. And this is again, probably a carbonate primarily. In freshwater, it exists primarily as a carbonate also. And primary form is bicarbonate. Why this? Okay, well, you're about to find out. Okay, why does it take this form? Why doesn't it exist as CO2? Why doesn't it exist as something else? I'm about to explain that. Okay, so first we got to answer this question for me, please. So imagine the Earth is perfect, pristine, primordial. No human impact whatsoever on the whole Earth. Human activities, no power plants, no nothing. Just everything is this primordial, wonderful place. No human impacts, no land pollution, no water pollution, and especially no air pollution whatsoever. The air is clean and beautiful and all that. Okay. When it rains in this pure, unspoiled land, okay, and the rain falls down, what is the pH of the rainwater?
Exactly 7.
At 7, probably 5.6. Okay. What? Okay. Yeah. So more than likely it's going to be 5.6. Okay. And this is what I was talking about in lab. What happens? Okay. You have this what is known as the carbon dioxide, carbonic acid, bicarbonate, carbonate equilibrium. It's often referred to as the bicarbonate buffering equation. Okay. So what it is basically there are 4 forms of dissolved inorganic carbon. CO2, carbonic acid, bicarbonate, and carbonate. So these are all the 4 forms that exist in water. What happens is when water and carbon dioxide come together, and again, this is what I mentioned in the lab, okay, it's an equilibrium. Some of these molecules join and they form carbonic acid. Some of these break apart. So basically, in this form you may have lots and lots of CO2 and only a little bit of carbonic acid, but they're in equilibrium. So if I add more CO2, I get more carbonic acid. If I take away CO2, this goes down. This equilibrium exists constantly. We're just getting started though. There's also an equilibrium of carbonic acid with bicarbonate. So what happens here is this splits apart, drops a hydronium, and you get this anion too. So they're in equilibrium. So I got these 3 piles now going. As I raise this one up, the other 2 raise up. When I push this one down, the other 2 push down. So we see nice equilibrium. It doesn't end there because bicarbonate is in equilibrium with carbonate, and it frees up 2 hydroniums here. So all these things are working and staying at certain concentrations at each time. Okay. So in each equation, if you add one of the 2 components, you increase the concentration of the other. So if I add HCO3, I'm going to make more CO3. If I add HCO3 in this equation, I make more carbonic acid. If I add a carbonic acid here, I make more carbon dioxide. If I add more carbon dioxide, I make more carbonic acid. So and they would just go up and down. They all kind of float together. Okay. So it's the same thing. If you decrease one of the 2 components, you'll decrease the other one. Okay. So when I put this whole equation together, this is what it looks like. So CO2 and water are in equilibrium with carbonic acid, which is in equilibrium with bicarbonate, which is in equilibrium with carbon. Okay. So as I start pouring carbon dioxide into water, what that does is that increases the amount of carbonates. That increases the amount of bicarbonates. That increases the amount of carbonate. But at the same time, I've got something else in that equation too. As I add carbon dioxide, I'm increasing the amount of hydronium ions here and the amount of hydronium ions here. I'm increasing the number of hydronium ions. So CO2 is added, carbonic acid increase, carbonate increase, bicarbonate increase, carbonate increase. Okay. So the equilibrium is being pushed to the right when you add. Okay. But likewise, I'm increasing those concentrations of hydronium ions, and there it is, which means I'm decreasing pH. So even in a pristine, perfectly clean, vector unspoiled world, as pristine way it passes through the atmosphere, it's going to be passing gases of carbon dioxide. Maybe not as many as we have right now, but there would be carbon dioxide. It picks up the carbon dioxide and drives that equation to the right and lowers the pH. So the point here is that rainwater is naturally acidic. People talk about acid rain. Yes, it's acid rain. It always is acid rain. It's been acid rain since the beginning of time because of this equation. It's always acidic. And that's kind of important, actually. Okay. So inorganic carbon concentrations influence pH in aquatic systems. Okay. Likewise, pH influences inorganic carbon concentrations. So if I lower the pH, I'm going to drive the equation to the left. So here's what I'm going to do right here. So at high pH, okay, so at high pH, the equation is driven to the right. And what that does is that basically the DIC is primarily carbonates. At low pH, the equation is driven to the left. If I start adding lots and lots of these hydronium ions, they're going to be these are going to be hooking up to make these are going to be hooking up to make these, and these are going to be coming apart to make this. So under low pH, the equation is driven to the left. Okay. And at that time, then what I find is that the carbon dioxide in the system is primarily here. When I drive the equation to the right, carbon dioxide is primarily here. Carbon, rather, is primarily here. Okay. So this is basically what they're showing you here. These are forms of organic carbon at different pH levels. So if we look at pH, so when pH is very, very low, most all the carbon will be carbon dioxide. Okay. When pH is very, very high, most of the carbon is going to be carbonates. But here in the middle, which is really, this is realistic. You don't find streams with pH of 11. You don't find streams with pH of 3, at least not naturally. Okay. The highest amount is basically the bicarbonate. Okay. Usual lake pH right about there, 7 to here, in that zone here. So HCl3 is going to be the most prevalent form of inorganic carbon in lake systems. What will be the most common form in acidic systems? Okay, a kind of interesting story there. Okay, we'll talk about that in just a second. It's kind of an interesting story. Okay. All right. Now, this is my story. Dr. Greenwood, I believe, talked about mixes in lakes. Dimictic lakes, right? Monomictic lakes, polymictic lakes. Okay. What is a monomictic lake? A monomictic lake is a lake that overturns once a year. Lakes around here are monomictic. They stratify in the summer. It gets really, really hot. The surface water gets very, very hot. The bottom water stays cool. And so you stratify. When fall starts, which we're having to right now, the top cools down enough and the lake mixes all through the fall, all through the winter, all through the spring, and then stratifies again the next summer. So our lakes are monomictic. One period of mixes per year. A dimictic lake, those are northern lakes. Okay, they have 2 periods of mixes. So during the winter it gets so cold you get an ice cover, and so now the warm water is at the bottom at 4 degrees C, and the cold water is at the top at 0 degrees C. This water is weird. And then, so it stratifies in the winter. Spring comes, and you get mixes all spring. Then you get that summer stratification again that we get with the warm water on the top, cold water on the bottom in the summer, and then in the fall it mixes again. So that's the dimictic lake. What is a polymictic lake? These are shallow lakes that the frequent periods of mixes. So basically you find them in hot areas where they quickly stratify, but they're shallow, and so if you have a storm event or something like that, they quickly mix. So there's no real mixing pattern for that. Add to this picture then, okay, So these are all considered, these are all considered what? Holomictic lakes, because they truly mix. The whole thing mixes from top to bottom. Enter a new kind of lake. Okay. Meromictic lakes. What do the meromictic lakes do? Okay. These are lakes that are stratified, and they never, or about never, completely mix. So there's mixes occurs, but it's not the whole lake. It's not from top to bottom. You've got a dead zone in this lake. Okay. Oftentimes these lakes, one of the characteristics about them is they're very, very steep. They're not big lakes. They're relatively small, but they're extremely deep and with very steep sides. So as a result, you don't get wind turnover or anything like that. You get deep, deep water, which is never going to get, you're never going to get warm enough down. No matter how hot the day gets, it's not, you're going to have, it's going to remain stratified forever, or almost ever. Okay. Also, the stratification is not based just on temperature. Oftentimes these lakes, bottom water is saline.